All right, hello everybody, and welcome to the Tech Report podcast live stream. We are here with David Kanter of Real World Technologies. Say hi, David.
Good evening, everyone.
David is a CPU and basically chip architecture expert who writes some great stuff at Real World Technologies and for the Microprocessor Report. And he's agreed to join us here to talk about what happened this week. Mostly, we're going to talk about AMD's Analyst Day and the new information that they disclosed around their Zen processors and upcoming graphics chips and all of that. So we may be doing some handicapping on some of that stuff. And David, thanks for joining us.
Yeah, it's a pleasure to be here. The only difference between this and one of our normal get-togethers is now it's being streamed.
Right. We kind of do this fairly often and get together and just like talk about what we think is going to happen. And so I've always thought it would be good to capture that because those are some of the best discussions. So we're going to make an attempt to do that here tonight.
Yeah.
So I should say before we get into the discussion that tonight's podcast live stream is sponsored by ASUS, and we actually have a thing on the site about this. We are giving away, thanks to their generosity, and a GeForce GTX 980 20th anniversary gold edition, this is the highest clock GTX 980 that I have seen. And all you have to do to enter is go to the website at techreport.com, find the Enter to Win post, looks like this, answer one simple question that can be found on ASUS PC DIY website, put in your information, and you are going to be in the drawing. So, yeah, it's simple to enter. You only enter once, but do it. Your odds should be reasonably good. I don't know how many signups we have yet, but it's probably.
Am I allowed to enter?
Yeah, but I totally won't. If you get it, I totally won't award it to you. Because I'm not allowed, and you're too close to the staff. I don't know. Actually, I have to think about that. We could talk about that. But if you need a video card, talk to me later.
Yeah.
I think we could probably help out with that one way or the other. So, anyhow, David, let's go ahead and get into we're going to have questions from the chat. In fact, guys, if you're in the live stream with us and you have questions for David or me or for both of us about anything really, but especially, the stuff that we're going to talk about this evening, then go ahead and put them into the chat. We'll collect them together and we'll try to talk about them and address them. But I think we know the general subjects that we have in mind. So I think we can probably go ahead and bring up our report on the Analyst Day, which happened, what was that? Wednesday, yesterday. And that was a long day for me writing that up and watching that. Did you watch the whole webcast?
No, I was actually in a meeting for most of it, but there was a number of us who were actually pre-briefed on it, and so I saw an early version of it, and then I got to see the slides afterwards.
Yeah, I did it. I did a pre-brief and then was writing about it, and then it came up, and I think it was over 3 hours by the time the whole thing was said and done with the Q&A.
Oh yeah,
that was exhausting, but there was good information about AMD's new stuff and their plan. It used to be back in the day that we got roadmap information out of these chip companies pretty regularly, pretty far ahead, and it wasn't always reliable, which really nothing has changed there, but now they don't disclose as much as they used to. So, yesterday was kind of a big deal just because I think it's been a couple of years since they did this much disclosure.
I mean, it's not just that, but I mean, AMD in particular, the most recent roadmaps that I think almost everyone had went up through 2015-ish. And so, there was a bunch of things where you could look at it and say, well, what are you doing for servers this year? And the answer was, well, don't really know. This is on the roadmap, but, it might have been that the most recent thing that was going to happen was in late 2014. So, I think it's good to get the update, and it would be really nice if we could get, a degree of specificity, maybe, Intel's pretty good about saying first half, second half, and you can make some guesses. And I think with AMD it's a little trickier. It was nice that they were pretty clear about when Fiji would be coming out.
Right, and Fiji is the next generation big GPU that they said a few weeks, right?
Yeah, well, I mean, what I caught was, second quarter, so there's not a huge amount of time left,
Right.
So,
Right. And we know they have a big event planned at E3 that they're already sponsoring. That's like sort of a PC gaming celebration thing. And so one would expect to see some news come out of that event around their new GPUs, right?
yeah,
And
I mean,
so
that
we
would
know
be natural.
roughly June 16th, 17th, 18th in LA is E3.
Yeah,
So probably around that time, we could probably expect some news.
yeah.
Yeah. So let's see. So that's true. The other thing that has happened is we have a new CEO. This was Lisa Su's, I think, first analyst day where she really sort of laid out her plan, which is a little different from Rory Reid's. Like she's from Rory's team, who he brought in, and she's retained most of the same management, right?
Yeah.
But this was her first sort of I'm in charge now at the top rodeo, right?
Yeah, so I mean, this was her opportunity to put her stamp on, the roadmap going forward and really be clear about where she saw things going. And, I think from that standpoint, it's good. And we can see some departures from what was previously planned. And I think what's interesting is, in some ways, the biggest changes may have been to things that were, to some extent, almost outside of Rory's control. I don't know how much of the roadmap was, to some extent, dictated by decisions that were made under the old CFO, I think Thomas Seifert.
Mm-hmm.
And that was one of the big problems with AMD, is that when they got rid of Dirk Meyer, there was really a vacuum in terms of power. And so when you have an interim CEO, it's very hard to commit to a strategic change in direction. So,
right. And well, and they have clearly, like, what we saw even this week is that we know what they're doing, and they're investing in a new Zen core, and they talked some about the Zen core, and we can get into that. And they are doing a new GPU. At least one of them is coming, but what we're not getting is like a top to bottom refresh of the GPU lineup, or a top to bottom like refresh of really stuff on the new core soon, right?
Yeah.
Basically, what they told us is, and we should probably get into the report here, but what they told us is about Zen, and then about one product coming in 2016 that actually will probably be one chip that'll be a couple products, I think, for different markets, right?
Well, no, I mean, so they were pretty clear that there's at least two chips in the works, right?
Okay, well, let's talk.
Yeah.
Okay, let's talk. I'm not sure about that for 2016, but let's talk about Zen, and then we'll talk about the chips based on Zen, because that's like the order of this article that I pulled up, and I want to make sure people understand what Zen is.
Yeah.
Because Zen is the successor of the Bulldozer family, right? It's an all new, from the ground up, or as they say, grounds up or ground up, which I don't know how that works, but all new design from the ground up CPU architecture, the x86 compatible, that is a big core that will replace the Bulldozer family, hopefully with something that is better performance and lower power consumption, or higher power efficiency, really is what you're looking for.
Oh, yeah.
And higher total performance, and maybe even fitting into lower power envelopes for smaller devices and laptops and tablets and things like that. So that's sort of, you can say they bet the company on Bulldozer and it didn't work out real well. It's a much smaller company now. Zen is their next bet, right? And as much as any time in the past, the company's fate relies on what happens with this.
Yeah, I mean, I think to a large extent that's true, and it is really, sort of the last hurrah in some sense. I mean, if you look at AMD, I think one of the things that's been very clear is that financially speaking, the company has not been in a good position for a while. I think they got really, it's not fortunate. I mean, it's a testament to the skill of the engineering and really providing what the market wants that they got all the console business. But, certainly for the last few, quarters and, probably the last year, that's really been the thing that's been keeping AMD along. And, it would be great if Zen could come out earlier, but the reality is that designing a new CPU core and validating it and lining up with, manufacturing at TSMC and ramping into volume, that's sort of probably a 5-year endeavor. So, what we're seeing is really the fruits of something that was probably started almost as soon as they could.
Right. Well, and you kind of trace that beginning back to when they brought on Jim Keller, right?
Right.
Who is the CPU guy who was behind, what did he work on at AMD first, K8?
Well, so he was at Digital for a long time, and then he came over and worked on a version of the K8, which actually never saw the light of day. And my understanding is that there was a very different K8 that didn't look too much like the K7, and there was a bunch of internal politics, some decisions were made, and ultimately sort of what ended up coming out was, take the pipeline of the K7, modify it to support 64 bits, and, make some significant improvements, add SSE to support, and then integrate the memory controllers and hypertransport. And, I think originally it was a more ambitious of a project. And so then, Jim went to
Apple.
Well, no, before
eventually.
that, I can't remember if he was at SciByte, but he was at PA Semi.
Right.
Yeah, and so he worked on an out-of-order core there, and then he went to Apple, and then came back, after doing quite a few generations of, very successful processors at Apple. I mean, I'd say if you were to look at the world today and say who can design, demonstrably design high-performance cores, the list would definitely be Apple, Intel, IBM, and, say AMD for the sake of argument. Last one wasn't so great, but, clearly they've done it in the past.
Right. And so Keller was involved with Swift and Cyclone, which turned out pretty well.
Yep.
I believe. And then he goes back to AMD and they start this effort with Zen.
Yeah.
And they're not just developing one new microarchitecture either, right? Because they've got K12.
Yeah. And so that's one of the things that's really interesting. I mean, there's a lot of similarity that you can have between, say, an ARM and an x86 core, but, the actual UOPS and fundamental formats and the way you handle your memory pipeline, those are going to be different. And so I think it'll be interesting to see what comes out. And I think they'll look very similar. But my guess is that it's actually quite a lot of engineering work that's going to be unique to each. I mean, I was at a talk from Intel where they were talking about how much RTL, how much code that is written to describe the microprocessor gets reused from, like Nehalem to Westmere or Sandy Bridge to Ivy Bridge. And I was really surprised because they said that, on a good shrink, maybe we get 30% reuse. Sometimes as low as 20. And so to move architectures, that's kind of a big deal.
Right. Well, it seems like the plan is different architectures and maybe some sharing, but clearly with the different ISA, like you can't share a lot. And then the plumbing on the chip around the cores would probably be shared, right? So PCI Express and memory, I/O, that stuff.
The on-chip fabric and power management. I mean, frankly, the biggest reason for AMD to go out and design their own ARM core is that the standard ARM cores have very limited options in terms of really interesting physical design versus logic design trade-offs and power management. And, Sam Nafziger's group at AMD has done a lot of really interesting power management, but it really does require hooks into the core to get measurements for activity. And, the strength of what ARM provides is that you can basically take it unmodified and try and tape it out, which is, what a lot of folks like Allwinner might do. But the challenge is you can't modify what they have. So if they don't provide some sort of standardized interface for, say, measuring capacitance and figuring out how many transistors are toggling, you're out of luck, and you can't really start thinking about more advanced hardware power management, which is really where things are going in the future. I mean, that's where Intel is, that's where IBM is, and that's where everyone would like to go.
Well, and it seems like that for AMD, the opportunity with ARM is also that the other ARM cores that are playing in like the server market or anything that's not Apple are pretty small compared to the class of core that we're talking about with Zen or K12. Right?
Yeah, I mean, at the high end, there's going to be a fair number of ARM vendors out there who have pretty serious efforts, but Cavium has a very small, lightweight core, but they've got a lot of them, which is a great fit for networking, which makes sense given their background. Broadcom actually has something that on paper sounds like Haswell. The reorder buffer is on the order of 192 entries. The load store buffers are really big, but just sketching out a design on paper is something I can do. It's how does it really tape out and how does it work? And there's been some indications that there's some teething difficulties there, but Broadcom certainly has some high-performance MIPS cores, and they could do a high-performance ARM core, and it sounds like that's what the plan is. So, those are AMD and Broadcom are really the two that seem to be clearly oriented towards higher performance ARM cores. And then sort of the big question mark is Qualcomm, which is indicated that they're going to do servers, but there's really not much in the way of details, but we do know that they've been designing their own ARM cores for quite a number of generations, and they seem to do very well in phones.
Right. Now, Crate was good, and they've got presumably 64-bit something coming soon. So let's talk. We should probably talk x86 because most of the disclosure was around that. I think the big news from AMD about K12 and ARM was that it's coming later because they prioritize Zen.
Yeah.
So the Zen products happen next year in 2016, and then the first K12 chips come 2017-ish.
Yeah.
Or maybe later. They said something about sampling in 2017, I think. So,
right.
So what they're doing is going back to roots, I think, and building, competing against Intel. And so what we got, I think we got basically like just a few tidbits about Zen. So let's put them here. The one of the most interesting ones is this one here, where they say they're going to have a 40% increase in instructions per clock between the excavator core, which is the latest bulldozer, which is in Carrizo, which is not even launched yet. It's their next APU. But they're saying they're going to have a 40% increase from that to Zen. And beyond that, then they'll continue to refine Zen. They have a roadmap going forward where they go beyond like higher IPC.
Sure.
And so we got that. And let's just bracket that for a minute. So a couple other things. They said that they have simultaneous multi-threading, so they have 2 threads per core, which is looks a lot like Intel's hyper-threading on Haswell and Skylake. And then they have high bandwidth.
Well, hold on. Has Intel actually said that they're only doing 2 threads on Skylake?
You know what? As I said that, I thought, we don't know.
I mean, they could.
They could do more. That's the thing about multi-threading is SMT can be more threads per core than just 2. But AMD was specific about Zen is 2.
Yeah.
Right. So they've also got high bandwidth, low latency cache, which those 2 words are good, and delivering on some of that promise would be an improvement from Bulldozer, right?
Yeah, I mean Bulldozers. If you had to pick one piece of Bulldozer to say that was messed up, it's their cache hierarchy.
Right.
the combination of a write through L1 and a single, transaction L2, they can only do a single read or write at a time, is just really catastrophic, especially because you've got, what that means is that you have all the stores from two different cores have to be hit the L2. And not only that, the latency for the L2 is pretty high because of the physical design. I mean, I remember talking to some of the guys who worked on it, and I was like, so, you have this really great array design for the cache, what gives with the latency? And the answer was, once you get to the request into the cache, we get the answer back really fast. We can't speak for anything else.
Mm.
So I mean, I think really what happened is, they're going to probably go to a write back L1 cache, and they're going to have a much better design. And, that's great. I mean, I think that's really important.
Yeah. Now, the other thing that we got, 2016 availability for first products, and they're going to be based on a FinFET process, which is the 3D transistor structure that Intel has had for a couple generations. That everybody else has struggled to get out, but it looks like they're starting to run production. At least Samsung's doing it. TSMC seems to be about there, right? And
well, so Samsung, yes. TSMC, no. I mean, right? We can go out and buy parts made in Samsung's process, but the important thing to note is that there's a real difference between Samsung Semiconductor designing chips on their own process and someone else doing it, right? And the interface there is just not as smooth. And so when you look at what's going on, Qualcomm and a bunch of other folks are going to be using Samsung, but they're going to be a couple months behind. But I think the important, and Apple too, is certainly the rumor. I think the important point is that, FinFETs are a huge advantage in terms of circuit design. They let you drop your voltage a lot and reduce your VT because you get better control over the subthreshold leakage.
VT
and
being
it just
voltage
does a huge
threshold.
number of things.
Right.
What did you
so
say?
Basically, you can operate at lower voltage. And that means less power consumption.
Yep.
And it means better idle power, and also just less leakage, right? Which
is
the big one, I guess, in a lot of ways.
Well, in some sense, that's actually the the key to the FinFET is that with a standard transistor, turning it off is kind of like stepping on a garden hose, like in the middle of your grass lawn. And I mean, you can step on it and you'll close off most of the water flow. But, a FinFET acts a lot more like a vise on three sides. And the real thing that it does is it lets you get way better control over the transistor as it goes from off to on. And by doing that, you can move the threshold voltage lower, which is what lets designers move the actual operating voltage lower. So that's sort of the way it works, and that's one of the reasons why there's a lot of grousing by people about the fact that, well, gosh, these new Intel 22 nanometer and 14 nanometer parts don't seem to have much better top-end frequency. And to some extent, the reason behind that is the semiconductor physics of the device.
Yeah. But they're way better at low voltage operation, and that's where we've seen the benefits. And clearly Intel has proven those. Everybody else is getting there, trying to get there. So here's the question, right? AMD says we're going to have FinFETs, and it seems like there are several candidates to be producing this chip for them, and they didn't say who, right? So it could be TSMC on 16 nanometer FinFET process. It could be Samsung on their 14, which is really they're about the same size, but I think TSMC didn't want to call it 14 because it's bad luck or something.
I have no idea.
And then there's also Global Foundries, who has been making most of AMD's CPUs, who has had real trouble getting to 14 nanometer FinFETs, but licensed the process from Samsung, right?
Yep.
So who do you think makes? Do you have a guess? Do you have any idea who makes that chip for them?
I would assume that they're going to have to do a fair bit of business with global foundries. But I would expect them to be using both global and TSMC, realistically. I mean, the GPU guys have been using TSMC forever. And so, when we talk about, beyond Fiji, they're going to be working with graphics IP on both global foundries and TSMC. I'm sure that they would like to make sure that the processor can be done on both. But, there is a little bit of a hit there in terms of performance, in that if you customize for one architecture versus the other, you will get better performance. So I would assume that they'll probably do global to start with.
Okay. Well, so here's the thing that we want to know about is that's the basics of the disclosures about Zen Core. We can talk products in a minute, but first, everybody wants to know about the one performance claim that we have, which is the instructions per clock, or IPC claim, 40% higher than Excavator. So what do we make of that? Hey, is that enough to compete with Intel? Because Intel's going to be shipping presumably Skylake or Cannon Lake. Is that what comes after that?
So this Skylake comes out this year, right? Probably second half. It really depends on where they are. I mean, I don't expect high volume from really anyone except. I don't expect high volume to be available to AMD until sort of first half of 2016. When I look at what's going on with Apple, Apple's probably going to soak up a lot of chips from both Samsung and Global.
So you're saying that even if AMD were ready, they probably couldn't get enough chips made until later in the year.
Well, I mean, it's tricky, right? At the 28 nanometer node, there was all sorts of capacity constraints and just, problems going on there. And, that it wasn't a TSMC problem per se. It was really, there's just way more demand than TSMC had supply. And so I can see that happening with some of the FinFET processes, especially for anyone who feels a need to compete with Intel. It's tough competing with one hand behind your back in terms of density and performance, because the other thing to keep in mind is that even though these FinFET nodes will have FinFETs, the metallization back end is going to be 20 nanometer density. So I think when we realistically look at it, everyone's really going to be very eager to move to it. And it's, a company like Apple and Qualcomm are, two of the largest fabless companies in the world. They use more wafers than pretty much everyone else. I think MediaTek might be bigger than Apple in terms of wafer consumption. But those guys can throw around their weight and say, I'm sorry, you thought you had other customers that mattered in Q4? You clearly didn't read our agreement.
Right. Well, so that's a problem for AMD, but let's handicap this IPC thing. Well, I think what you're getting at is if they have to wait on wafers, then that changes what Intel product they're competing against.
Exactly.
But and that's really, Intel is going to have the same basic microarchitecture. One of the Lake ones, right?
Yep.
But it's going to be either a 14 nanometer process or a 10 nanometer process. So let's just maybe not handicap Intel too much, but just ask the question about, say we're competing with whatever Intel has, like Skylake, Cannon Lake, whatever, something in the midpoint, something, I don't know. Is a 40% increase clock for clock from AMD, assuming 3 gigahertz plus clock speeds and reasonable power consumption, is that enough for them to be competitive with Intel?
And that's a really good question. I mean, so one of the disadvantages of not having Carrizo out, as you mentioned, is that, you haven't had a chance to take it for a test run. We don't, before this, I actually went on the Spec CPU website to try and find something on AMD processors, and almost everything dates back to 2013 there. It's really quite unfortunate. So it's very hard to say. I mean, I think one of the more interesting questions is, well, how much of that IPC gain is actually single-threaded? Because, as you said, we know that they've got simultaneous multi-threading, and that can be a pretty big boost in terms of IPC.
If you're talking about instructions per clock going through the core,
yep.
When you have 2 threads instead of a single thread.
Yeah.
But what we really want out of the processor is not just 2-thread performance that's nice, but single-thread performance that's nice.
Right.
Okay.
Yeah, and I mean, especially from a client standpoint, you know, one of the things that, and you've talked to Ronak at Intel a ton, he's always very careful to say that Intel really wants to focus on optimizing the performance per core.
Mm-hmm.
Now, that's not just single-threaded performance. And, you know, having good throughput per core really matters for servers. But obviously, in the context of a client workload, you know, despite what all these goofy phone manufacturers doing 8-core designs might think, you know, you're probably at your sweet spot with somewhere between 2 and 4 threads, and you really just want as much performance as you can get on those. So, you know, my big question is this 40% number inclusive or exclusive of the SMT? Because I could easily see multi-threading being worth, you know, 15 to 20%.
And so it's worth about 30% on Intel, isn't it?
Sure. Well, it depends on the workload. I mean, I've seen workloads that gain 50%.
Well,
now, that's like a straight server workload.
Right. Throughput-based stuff will do that for you if it's really nicely threaded. Yeah. So, but generally speaking, I think you could say that you've got somewhere around a 30% boost from the best SMT stuff from Intel. But yeah, so what we're hoping for is really more per thread performance, not just more threads per core and more core IPC.
That's
because their problem hasn't been, at least in the client space, multi-threaded performance. That even their current FX stuff is reasonably competitive with like the higher end Core i5s in really well-threaded workloads. But as soon as those workloads start to depend on the performance of a single thread, like all games, then they're in trouble.
Yeah, exactly.
Right, and so what they need is per thread performance. So we're hoping for more of that.
Yeah, and again, so, you know, if this 40% IPC gain includes multi-threading, then it's possible that we may be looking at a, you know, single-threaded, one-thread IPC increase of, you know, at the low end, probably 15%, but realistically, probably more like 20 to 25%. And it's also going to depend on, you know, the code that's running.
Yeah, but what you said there is really important, right? Because we got a claim from AMD that sounded really good with 40% IPC increase. It sounds like the beginnings of, if we can draw out a whole picture of good clock speeds and reasonable power consumption, something that, if not beating Intel's latest cores, is competitive, right? But the problem is that if they're getting that gain, if they're counting that gain on the backs of simultaneous multi-threading, 2 threads per core, then it's not nearly as large performance increase the place you need it most, which is single per thread performance.
Right. Yeah, I mean, like in your last review of AMD processors, I mean, how big was the gap in single-threaded performance?
It was substantial, and it was a little bit frustrating to see, right? Let's see, we can pull this up, and I think there's a graph that illustrates it best.
So I see an FX 8370 review, maybe?
Well, let's go right here, and let's just go straight to gaming performance, which is not always, like, games use up to around 6 threads now reasonably well. But they're often gated by the performance of a single thread, especially in our 99th percentile frame time metric, which is getting that sort of hairy sort of edge of the worst case type of scenario where some frames are getting delayed because of a CPU bottleneck, and that bottleneck is often a single thread. And so what you have in this case is the FX 8350, which is the latest core that they brought into this socket, is slower than the Core i5 4590 and that's their fastest thing at pretty like well over 4 gigahertz. And then you go up way up here, and you have the Haswell that's at 4.4 gigahertz, and so they have an issue that they have to overcome a gap that's pretty large by gaining that basically they need to gain a combination of clock speed and per thread performance.
Yeah, I was just about to mention that, is that, while Intel and AMD, most people except for IBM basically have kind of settled on 3 to 3.5 gigahertz-ish as like a sustainable frequency at the very high end. But, one of the things, and this goes back to my point about hardware power management, is, Intel can crank the frequency on a single core up to, 4.5, almost close to 5 gigahertz. And realistically, AMD probably can't do that. And one of the big reasons is just if you look at the process technology that Intel uses, it's very much optimized for CPUs in terms of the metal interconnect stack, and the transistors are going to be higher drive strength. So there's going to be at an intrinsic deficit from process technology.
Yeah.
But they should definitely be able to, improve their power management with a better microarchitecture.
Right. And so, we've seen people in other segments, we've seen Apple and mobile and folks like that do well against Intel without having the process technology advantage on the CPU side. It's a little bit different game than high-end CPUs where you're trying to switch quickly. But people have been able to do it. But this is different from the old AMD because the AMD used to own its own fabs and use very CPU-specific silicon insulator, like really CPU-specific processes, and they don't have that anymore. Like that's right. Right. So yeah, that's an issue. Well, let's talk about it's always troublesome to compete against Intel, I guess is the message. Let's talk about the products though, because I want to get your take on this, because I think what I'm seeing is this. This is what I took out of it. They said basically in 2016 they're going to address the server market with a new Opteron that will have many cores and be high bandwidth with lots of I/O. And they said they're going to address the high end of the desktop market with the product that has many cores and goes into a socket called AM4 with DDR4 memory, and it will share that socket with their next generation APUs, which will be chips with integrated graphics. Those APUs will not have a Zen core in them. So basically the only Zen-based products we get for 2016 are the Opterons and a high-end desktop with no graphics. Yeah. And so my contention, David, is that means you get one chip out of them that gets deployed multiple ways. We've seen this playbook from AMD in the past, and we see it from Intel with like Haswell E and EP. It's a single multi-core chip, fairly big cache, lots of I/O, and you deploy it into servers, and then you make a desktop version of it for the high end. Yeah. That's one piece of silicon for 2016 based on Zen. Are you thinking there's going to be more than one?
Well, I mean, the roadmaps sure don't indicate that.
Okay.
I mean, and the other thing is, right, if we step back and look at what AMD is doing overall, when I see them delaying the K12, I see that as being they're voting with their wallet, right? They delayed K12 because at the end of the day, it didn't add that much to the bottom line compared to getting Zen out the door.
Right.
And I think what we're seeing here is basically an acknowledgement that, even if they're able to get leadership in your desktop or mobile APUs, that is a candle besides the sun that is servers, right? And the only time AMD has been consistently profitable is when they actually had serious server market share. And so I think they're looking at this and saying, well, look, no one else has shown up to compete with Intel yet. The Xeon D really locked down that market till 2016. we want to be there and we want to take 10% of the server market, 5% of the server market, and that will have a huge impact on our bottom line. I mean, I think that's what the plan is.
Those are chips that you can sell for a lot of money,
Sure.
$1,700, $1,200, depending on how good they are. And that means that you have really nice margins on them. Even if it costs you a lot more to make a chip than it does Intel for that market, you can still make a lot of money making a chip for $100 and selling it for $700, right?
Yeah. I mean, the right way to think about it is, I don't know the exact wafer cost for 14 or 16, but, it's going to be probably somewhere in the neighborhood of $8,000 to $12,000. So, you probably get 100 server chips out of there, maybe, if they're really big, something like that. And, as you said, if you can sell them for $500 a pop, that looks pretty good.
It's good business to have. So and on the desktop side, if they get anything close to leadership, they can command similar premiums over there.
Yeah, exactly.
So it all makes sense. And this is, I think, Lisa Su saying, this is who we're going to be. It is kind of a return to roots for AMD, but we're going to chase this first, and everything else comes after that. So that is interesting. It's potentially good if they get something out. And what we don't know is how that chip looks. Is it 12 cores? Is it more? I mean, Intel's already sporting like 18 or so, right? In some of their Xeons. And the question is, like, they have to hit a nice spot. What Xeon D is 8 cores. And do they target that? Do they say we're going to do 10 or 12 and we're going to go for a low power envelope? Or, do they actually even build something bigger?
No, I mean, I think they want to. So look, if I was in their shoes, I would say the target has to be competing with the Xeon E5. With in that time frame, it'll be a Broadwell EP, right? And that might be more tractable than competing with Skylake, in terms of single-threaded performance. But, I think that the point is, if we think about Broadwell EP, that's going to be Haswell EP plus more cores. So, it might be a 24-core part or 20-core part, something like that. And, they'll probably, the challenge for doing high-end desktop and servers is that servers can use 20 cores. Desktops, going more than 8 is just, frankly, way overkill. I mean, at that point, you're just selling to people who either have home workstations, in which case they should get a Xeon, or, are doing it for bragging rights. And so my guess is if I was AMD, I would do, I don't know, 8 or 16 cores and then do a dual chip package like they used to do back in the day.
Yeah, well, see, that seems like a distinct possibility, right? Because they know that they're going to share a package, share a socket on the desktop with their APUs, right?
Yep.
And so say you have an 8-core chip with 2 channels of DDR4 for the desktop, and then you take that, double it, put 2 in a package or more, right? And then you've got, 16 cores and 4 channels for a server product or more, depending on how you package it. That seems like a distinct possibility. It is tough because Intel's got, 3 different versions of Haswell EP?
Yeah, there's 3 different.
They don't make just 1 core, right? And one of them is the one they put on the desktop. It's the little one.
Yeah.
So, yeah, it is a challenge for them to sort of match up, right?
Yeah, well, the other thing is, keep in mind that when we're talking about 2016, I think I don't have the server presentation in front of me, but I'm going to guess that they might not have committed to doing a 2016 server based on Zen. I'm downloading it right now, so we'll know in a few minutes.
Oh, no, that was part of the plan. That was definitely part of the plan. Was 2016 next generation Opteron. You can see it right here on the screen if you're looking at the.
I can't really.
Based on next gen Zen core, high core count with multi-threading, disruptive memory bandwidth, high native I/O capacity. That's the thing that becomes, I think, both an Opteron and a high-end desktop.
So my guess is, maybe we'll see the desktop in the first half of 2016. One of the challenges is that multi-threading is real. Designing a multi-threaded processor is actually not all that hard. There was a joke that Glenn Hinton used to say within Intel, what's so hard? It's just, an extra flop and a mux, right? Which is, you duplicate your latches and your registers, and then you have to choose between them. The real difficulty is in validating it, and server validation is hard in general. They're much less forgiving of bugs, and it's more complicated. So it wouldn't surprise me to see that come in the back half of 2016.
Right, and AMD knows about that with the Barcelona TLB situation and all of that. They're familiar with what happens when you didn't get your validation, didn't catch something in validation.
Yeah. What's interesting is, I wonder what disruptive memory bandwidth means. Right now Intel's sporting 4 channels of DDR4, which is pretty high bandwidth. I wonder what's going on there. I mean, it would be kind of cool to see someone actually using HBM for a server part, although, I mean, you'd have to have a cache controller designed in. There'd have to be some real changes, but that would be pretty neat.
Well, I think that's what comes in 2017, and that's the only other chip that I got out of this thing that's a Zen-based processor. And that's a 2017 chip that I think will be, it's an APU for servers, and I think it will also become a client product. And they talk about that on this same slide. So let's introduce HBM, because HBM is what's coming in Fiji, which is probably the R9 390X graphics card as the first product. It's high bandwidth memory, and we've got a little diagram here. This is basically, you have on the same package stacked DRAMs, like multi-chip stacks, and then a GPU, right?
Well, it's a quick correction. So it's not, the package is not how they talk. So what you have is that interposer is actually a very cheap silicon wafer.
So that's right. Then that's in the diagram here.
Yeah, and so what the advantage here is that you get much denser metal wiring through your interposer than you do in the package, and better signal characteristics and so forth. So, yeah,
so
this is Joe Macri's baby, probably.
Right. And this is almost like integrating memory onto the chip. It's like the next thing to it. And
that's right.
That gives you lower latency, right? Because you don't have to go as far with the signal. And lower power use, right?
I mean, I don't know how much it'll really reduce latency because they're optimized. It's a GPU, so everyone optimizes for bandwidth. The big thing is way lower power. And I think there have been Hynix presentations where they've said 5x better, and AMD's claim was 3x better, which sounds pretty reasonable in terms of performance per watt. And I mean, it makes a big difference because you can also get rid of or reduce things that don't scale on I/O, like your ESD protection for electrostatic discharge. As long as it's just silicon to silicon, you may not need something quite as big. And those sorts of circuits just don't scale with process technology. So getting rid of them would be, a huge benefit.
And so AMD, you mentioned Joe Macri. He's actually got a CTO title over there now, I think. But Joe he's working with JEDEC, he's worked with Memory Technologies, and he shepherded to market multiple GDDR memories.
Yep.
And when he did that, then AMD won in that product cycle against NVIDIA because they had the best new memory tech first. And so what we're looking at for the R9 390X, I think, is the same thing where we have a new memory tech. I have a couple of questions about it, though, because I think we're going to see HBM on Fiji. And I'm hearing some things about it that could be disadvantages. One of them is that they're only going to have 4 gigs of memory in total because they've got it, like the capacity, the way that it's stacked and set up, that's the capacity they're going to be able to have, which isn't enough to match the competition's ability to stick more DRAM on a board, right? And with 4K displays being sort of a big marketing point, like that could be an issue.
Yeah,
I don't know that it will be. I think we'll have to test it and see if it really hurts, right? But that's been an issue. The other
I don't.
question is, well, another question is, what is the power consumption uh, contribution to a modern big graphics card
So
in terms of memory? Is the memory savings that we're talking about with HBM, or energy savings we're talking about with HBM, really a big portion of the overall picture?
yeah, I mean, so first of all, I don't think it's going to be 4 GB. That doesn't sound right to me. I mean, and if we,
Okay, that's reassuring, right? If they can do more.
yeah, I mean, my guess, and now I'm going on record for this, but I think it'll be more like 8 GB. I mean, certainly AMD. Look, I mean, they know what the display technologies are. They're not going to do something, to really spite themselves. It may be difficult to get 16 GB.
That doesn't matter. I mean,
Yeah, I mean, I've actually held a Fiji in my hand.
So you're on record and you've held one in your hand, but this
I
is all
had no
speculation,
idea how
right?
much memory it had. This is not
Okay, you didn't
inside
count,
information. This is just going from what I know of the HBM standard.
right?
But so your question was, well, how much of the overall budget, power budget, could your memory be? And
Right.
I don't have recent numbers, but I remember a few years ago hearing that a full-blown GDDR5 memory interface could be on the order of 50 to 70 watts.
That's substantial.
Yeah. Now, I don't know what's included in that. That may be memory controller and the physical layer interface. Could be a bunch of other things. But, I think the point is it is a really big portion of the power budget.
Right. So that's good. And also, I guess the other thing that you're hoping for in this case is just a crap ton more bandwidth than the other guys have, right? Like way more than GDDR5. So,
yeah.
And
actually,
you get that.
70 watts doesn't seem unreasonable if you think about it, right? Because each GDDR5 DRAM is probably going to burn a couple of watts, maybe 2 to 4 watts. I don't have the numbers off the top of my head.
Yeah.
And then on top of that, you have the GPU side of the interface is going to burn some more power to boot.
Right.
So, it could be that, 70 watts between both sides of the interface is not unreasonable.
So that's it's not the world, but it's a fair amount, even in the world of high-end GPUs, to save that much.
Yeah, well, I mean, that's like a quarter of your, it's like maybe 20 to 30% of your power budget. And so if you can now spend that on shaders, that's great.
Right, because shaders, relatively speaking, are power efficient. ALUs are power efficient. And the other thing you need, though, is you want that bandwidth, because in graphics, bandwidth is one of the big constraints, right? I mean, that is...
Absolutely.
Yeah. The thing that bothers me a little is just, have you seen, like, there's some leaked pictures of Fiji cards, and they look like they're water-cooled?
Yeah, I mean, you got to do what you got to do.
Yeah, but, I mean, if you got to do that, then, like, you've got to do a lot more, apparently, to evacuate heat than your competition.
Well, yeah, so I mean, there's two questions here, though, right? One is, what's the total thermal dissipation? And to be honest, I mean, for a high-end GPU, I don't think this actually makes a difference. When I'm playing a game, like, to me, getting the, I haven't played a game in a while, but, I'd like to play The Witcher 2, The Witcher 3 when it comes out.
If you're listening, send David a code for The Witcher 3.
It's more about the lack of time, but
okay.
The point is that I'm not going to begrudge my GPU another 20 or 30 watts. It's really about the PCIe power ins that I'm worried about. And so, anyways, my point is, as long as they don't go over 300 watts, they're probably fine. But the other question is, if you've seen the prototypes that NVIDIA and AMD have shown, they're way smaller than standard graphics cards. They're like half or a third of the size.
Right,
so it may not be
so much... Which is an HBM benefit, right?
It is, but, the downside of cooling something that's a third of the area is, well, now you've got a third less surface area to draw your heat flux out through. Right. So it could be that it's actually more of a thermal density problem and not a raw, oh my God, we're chewing through 400 watts kind of problem. It might just be, well, it's cheaper to do water cooling than to have like a, pure unobtainium heat sink.
Right. And no, that makes perfect sense. And I'm happy to use a cooler that takes the heat and lets me eject it directly out of the back of the case instead of just blowing it around inside, like a lot of the sort of fan-based things now do. So, so prospects look good for that. And that's HBM. That's sort of a prospect for Fiji. We kind of talk graphics, but let's take this back to what we mentioned, which is
hold on. So I did hear something interesting the other day.
Okay. Uh-oh. What was that?
So I was talking to Riss and some other folks, and it sounds like Fiji will be some sort of derivative of Tonga. Tonga's the latest.
Yeah, sure it will, which means it has the delta-based frame buffer compression.
Exactly.
And so it's got tons of bandwidth plus more memory efficiency. And that puts them roughly close to on par with what NVIDIA is doing with Maxwell on the memory efficiency side.
Yep.
But presumably they're going to have even more bandwidth than like a Titan X if
HBM
delivers. And so there's every potential for this product to be the fastest high-end GPU. Yeah,
well, I mean, right, I'm trying to remember the die size for Tonga, but...
Big. It was the size of Tahiti, basically, like an R9.
Like 380 millimeters squared, something like that?
I can pull this up if you really want to know.
I mean, this would be interesting to know, because we can just do some back-of-the-envelope calculations here. Don't forget to click on the banner ad, Scott.
I love this website, man. It's so useful. So there it is, Tonga, 359 square millimeters versus Tahiti 365.
Right.
So and anyway, there's all this stuff around Tonga that we should talk about. But anyway, go ahead.
Well, but the whole thing is, like, imagine you take away a bunch of area for the memory interface, because now you've got HBM, and that's going to be smaller, right? And then on top of that, AMD might be willing to go for a big die, especially if it's 28 nanometer. That's a really mature process, and they probably have no real issues pushing through, a 500 millimeter squared die.
Yeah, well, one of the architects there, Mike Mantor, who I think is pretty influential at AMD now. He's kind of said to me in the past, just like, I think you make it as big as the reticle. Like, you just do that.
Yeah, no. Well, that's totally the right thing to do. There's no question about it.
So, like a 600 square millimeter die packed with GCN ALUs, a really compact memory interface, some power savings from the HBM, tons of bandwidth from the HBM, and the Tonga Voodoo for memory compression.
Yeah, I mean, that looks like a pretty compelling product right there. I mean, going 600 millimeters squared might be, the thing is, Intel does stuff like that all the time, but there's a real big difference between what Intel can pull off in their fabs and what TSMC can pull off in their fabs. I mean, I'll just point out that there is not a single company shipping a large die on 20 nanometer right now, TSMC, and that's nominally a mature process. Air quotes there.
Yeah, but 28 is, I think, what we're probably looking at for this chip based on the latest rumors. And if they decided this is the risk portfolio we want, maybe one reason that they went with 28 is because they're just like, well, we'll just make it freaking huge, right?
Yeah, sure.
Yeah.
I mean, especially if they can sell, if they can, with NVIDIA, it's always easy to justify, these mammoth die sizes because, the answer is, well, we can sell it to the Tesla market for like $5,000. Woohoo! AMD, it's less clear of an example, but if they can make and sell a compute part out of Fiji, then that would definitely allay a lot of the concerns around large die size.
Right.
So, anyways, we had wanted to return to another topic.
Yeah, and I want to talk more about Tonga, but because I think I was wrong about that, and I've been insisting on some things, and it looks like Tonga is worse than I was able to accept, because they just did their whole, like, everything that isn't Fiji apparently is going to be like, there'll be a whole series of R9 300s that are basically based on old stuff. And weirdly, they even have like the GCN 1.0 chips, like the Pitcairn, as part of that lineup. So no FreeSync support, no color compression, like not much in the way of 4K support. Like there are all kinds of things that the world has changed since like late 2011 or whenever those came out, that they're still going to be shipping some of those. But the Tonga thing, like the as part of the rebrand, they took what was the R9 285, which is Tonga-based chip, and have an R9 300 something that's basically the same thing. And the weird thing about it is the specs are the same, and there's not like a higher one. We know Tonga has more shaders on the die than what they're exposing in the product. My contention has been that it also has probably another 128-bit worth of memory interface, or 64-bit worth of memory interface, simply because, no, 128, because because it's the same size as Tahiti, which is 384-bit.
Yeah.
Right? And they are only shipping a 256-bit product. But we haven't seen that yet. So it's like, as time passes, my prediction that there will be a better version of Tonga in the market gets more and more uncomfortable, because there totally isn't. And it could still happen. It could still happen. But that is the saddest chip ever if it's the same size as Tahiti and is lower performance and came out later. And the only good thing that it did was that it made up for cutting down the memory interface by doing color compression. But at the end of the day, the die size was the same. Like,
yeah, I mean, when I wrote my article about Intel doing 3.5s, I mean, part of the reason I made that prediction is I didn't, there's a real chance I'm wrong. And that's what happens when you're looking out ahead of the curve, which you tried to do. And I think it's a good thing you did it. And, being wrong is part of the game. You can't always get your speculations right. It is really weird, though, that...
It is.
I mean, AMD is not... on the graphics side, their biggest strength has always been physical design, working with the foundry, and they've been much stronger there than on architecture and software, frankly, historically speaking. And so to see a chip come out where, like, the physical design seems to be a little messed up, that's odd.
Yeah. Now, they lost a lot of people. And a lot of the physical design people are doing semi-custom work.
Yeah.
So we don't know, like, was this, like, just the B team making this thing? But why would you make it? That's what I don't understand. Like, it doesn't seem like it should exist, because it wasn't a substantial upgrade. In fact, it was a downgrade from Tahiti on performance. And that is weird. That is so weird.
Yeah, I mean, the problem is, like, at the end of the day with most chip projects, you only have, beyond a certain point, you either pull the trigger and shoot the project in the head, or you got to ship it. And that's it. Those are your choices.
But they shot everything else in the head. They haven't shipped a new graphics chip forever. Why would you let that one out, right? Why would that be the one that, like, you're like, okay, we're gonna go with this. It's slower than the other chip of the same size, but we're gonna launch this thing. It doesn't make any sense.
Well, maybe you and I will get invited to the Fiji launch, and we'll be able to ask about it there. Although after your last rant, I mean, they might not invite you. I don't know.
I will definitely be asking that question one way or the other. I just want to know, like, it's a mystery to me. Like, I don't understand why that exists in that form, and how come, like, the better one isn't out there. They did get, you know what part of the answer is? That chip is in the 5K iMac. And that alone, like you probably need that memory compression at that really high resolution to do good things. That alone could be a justification for that project going ahead.
Oh, I would think so. I mean,
and the 5K iMac version has all the ALUs enabled, has all the shaders.
Yeah, I mean, the other thing is that's also sort of consistent with, what Lisa said she wants to do with AMD, which is, they would like to not be the value player in the market and instead be in leadership products as opposed to the thing that you put together at a $200 price point. And, hey, what chips can you find that fit into that bomb, right? And so, I could totally see them actually going ahead with a project knowing that, the only real customer is going to be Apple. And I can also see that being a good thing long term for them, especially once they, have a competently designed CPU and maybe a broader GPU portfolio. But, I mean, as you said, it sort of seems like Tonga is the bulldozer of GPUs right now.
Yeah, it isn't good, man. So, okay, we've moved far afield on graphics, and that's great stuff. And I think we kind of have covered it. The only other thing they said about graphics is that in the future, not Fiji related, but in the future, that they'll have a 2x increase in power efficiency on future generations of GCN, which is just precisely what they have to do to keep up with NVIDIA and everybody else.
Well, I mean, that's also what you would expect from FinFETs, right? Because FinFETs generally let you, they will let you significantly drop your voltage, maybe by 200 or 300 millivolts. So, right there, that's, baseline 40% improvement, maybe up to 60 or 70%. And they haven't, there's architecture tweaks they can deploy. They can use more area, maybe, although that would be expensive on 14 or 16.
Yeah, they're not going to do that.
Yeah, but I mean, they should be able to get that moving to 16 or 14, no problem.
Right. So it could be process tech. I expect that they're doing some architecture design work around that too. But
HBM2 also.
Right. So there. Anyway, that was all we got on graphics from them. But what we did get, let's take this back. So we established HBM has some nice properties because it's smaller, it's higher power efficiency, higher bandwidth. Packaged closer to basically on an interposer with the chip, and it can be it's starting out in GPUs, but it could be used in SoCs, it could be used in CPUs, and they kind of talked about that, and that's what there's only one other chip that I got out of this roadmap information that is definitely happening on the CPU side, and it is a 2017 product right now. But it's this high-performance server APU that they have in their data center roadmap. The client roadmap did not go to 2017, but I think that there will be a client version of the same thing. It's going to be the same playbook as a lot of other things where you build it and then you sell it into multiple markets. But what they're talking about here is not the APU that we're used to. This is multi-teraflop combination of Zen CPU cores or Zen Plus or whatever it is, and then like a lot of Radeon shaders. And the way that works, the way that actually isn't terrible, and it gives you high performance, is that you bring more memory bandwidth to the chip. And the way you do that in a socket is HBM, which is why they have this transformational memory architecture under this high performance server APU. Not disruptive memory bandwidth, but transformational memory architecture, which I think means HBM. And so that means that they are potentially selling a chip, David, that I think that goes to compete with, like in HPC and supercomputing with NVIDIA and Intel, with Xeon Phi and all of that.
Maybe. I mean,
no, I mean, that's what they want to do. Like,
I mean,
they hinted at this. I'm not saying that they're going to win. I'm saying that's what they want to do. I think I'm right about that, even if they're wrong to do it.
I mean, so right, the big challenge in the HPC world and is you need a solution.
Right.
And if you look at the top 500, which is about probably a third of the HPC market, a lot of it is InfiniBand. A lot of it requires an extensive software stack. And I mean, look at NVIDIA. I mean, they've been working on this for almost a decade or now. Yeah. And they still don't have comprehensive application support. They still, have an incomplete tool chain, especially compared to Intel. And so, when I look at a lot of the work that AMD's done, I think it's great. I think HSA is good, but it fundamentally doesn't solve the problem that in HPC today, the way things work is if you want a GPU, you use CUDA. For everything else, there's x86, and then there's some niche IBM stuff, right? And so the question is, what does their overall solution look like? We know what NVIDIA has. It's going to be, NVIDIA GPUs, IBM CPUs, and then Mellanox InfiniBand. And, for Intel, you have Intel Xeons, you'll have Xeon Phi, which can go by itself, by the way, and has, there'll be versions with co-packaged fabrics that are 100 gigabits per second, right? What is AMD going to do about the fabric? Who are they going to work with?
Oh, but did you catch this? I don't know. You didn't. Okay. So first of all, I think the answer to the question of what is their solution is that they're going to do a high-performance server APU because they called their shot. Whether or not it's a good idea, and you know what, that thing like a Xeon Phi can go by itself, right? It's an independent processor, not just a coprocessor. It's not just a GPU, right?
But how do I hook up 50,000 of them together?
Right, and that is the interesting thing. The only thing, in fact, Mark Papermaster is so guarded. He's the head CTO, and he talked about this stuff. He's so guarded, he didn't give us much of anything. But the one thing that he talked about that was interesting is, he has moved AMD in a direction of building their chips in modular fashion. So each IP block, graphics, CPU, accelerators like the video decoder, all basically are interchangeable, and they talk to each other on a common fabric. And that fabric is an internal AMD technology. And I think it's probably based on hypertransport with extra stuff, but I'm not sure. He said something about we had an existing solution that was good and we extended it, and I don't know what the existing solution was. Maybe you... Anyway, but here's what he said that was interesting, is that it now, going forward, they're using that to glue together all their IP blocks so they can be more modular and
oh, yeah.
But he said it also works off chip as a chip-to-chip interconnect.
I mean, that's
I'd never heard that before. But I mean, that could be part of a solution that gets you.
That won't buy you much, right? Because I mean, the problem isn't going chip to chip per se. It's let's look at the stuff on the top 500, right? We've got tens of thousands of chips. You need switches. You may need routers. I mean, you're going to have, and it's not, when people say chip to chip interconnect, the question is, how far does it go? If it goes if it goes like half a meter, that's fine for a motherboard. Even 20, 30 centimeters might be fine for that. But, if you want to try to go half a kilometer inside a data center or a kilometer inside a data center, you're talking fiber optics, right?
Yeah, you got to be optical. Yeah.
Right.
No,
and so AMD doesn't have any background in that. So they'll have to work with Mellanox. But, Mellanox is very much in bed with, IBM and NVIDIA. So,
but if you have a working standard for a link and a protocol and all of that, you can go optical with it by working with a partner like that, right?
Yeah, I mean, you would be using Mellanox InfiniBand cards and their switches. I mean, it's just that there's a lot of infrastructure that goes into HPC, which AMD has not invested in the same way that NVIDIA has, or that Intel, has and inherits by virtue of being fully x86 compatible, right? I mean, if you want to use this GPU, you can't just say, well, okay, let's poke it with AVX3 like you can Knight's Landing. So I'm not saying it can't be done, but I am saying I have a bunch of questions, and there's holes in the story, and so that they've got to be filled in. Otherwise, it's just it may not be super credible. I mean, they'll definitely get sales for sure, because there's a lot of things where AMD may simply be the best performance, and there are parts of the market where they'll say, it doesn't matter that they don't have the software. We'll write it ourselves. Like, I
Right.
hear the NSA is totally okay with that.
Well, and the other thing is that this type of a high-performance server APU can serve some roles that aren't HPC and supercomputing, that actually you could sell a lot of, right? If you've got a data center for cloud-based gaming, that becomes a thing, and you need to have like a bunch of gaming nodes that you host that are running AAA games that the video then gets streamed out, remotely across the net, then something like a high-performance server APU could serve that role potentially quite nicely, right?
Absolutely.
And also just like a remote workstation or a virtual workstation that is running in a data center that someone connects to, it could do that. And that sort of takes us to the other place that's this type of high-performance APU gets deployed, which would be desktops, laptops with higher power envelopes, all-in-one systems, things like that, right? Because because what you're talking about, if HBM gives you enough bandwidth, and if you pull this off, is something that's like a pretty like a mid-range gaming PC in a relatively small, because HBM gives you a small package, right? Relatively small footprint. Which is way different from today's APUs where they talk about gaming, but then you don't want to do it on them. Right? It can actually be good. And if it's good and low power and compact, then they could sell that and they could have something that Intel doesn't, right? Assuming that Intel doesn't build something similar.
Oh, yeah. Well, from a fundamental level, the only thing that a GPU brings to a table over a CPU is more memory bandwidth and a higher power envelope, right? If you look at a discrete GPU versus a CPU, at a very high level, that's the difference. And so the cool thing is, what AMD might do is say, well, hey, we've got the high bandwidth memory. We've got the bandwidth solved. Let's make an APU that's going to blow 150 or 200 watts, right? Because at this point, once you have the memory bandwidth solved and you're on die with the CPU, there's a bunch of cool things you could do with, an API like Mantle in terms of, really high bandwidth submission of draw calls and triangles and so forth.
And there are a lot of APIs like Mantle out there now.
Right. Well, there's by the time they're out, yes. Right. D3D12 isn't quite out yet.
No.
But I think the point is they could basically make a single chip that would be the equivalent of a very mid-range, $150, $200 graphics card if they wanted to. They just need to crank up the power.
Right.
And that is pretty cool and exciting.
Yeah. So that could be a good product. They're basically you're making it for 2017. Like a lot could change between now and then, including the schedule. But that seems like that's the plan. And that was about what I got out of the disclosures that they gave us around this analyst day. Like, I think that was pretty much it. But you know what? Let's do a couple things. First of all, let's one more time. Let's just talk about our sponsor for the stream, because I should be doing that. Because we have Asus sponsoring us tonight, and let's see, not that Asus. We are giving away, courtesy of them, a GeForce GTX 980 graphics card. It's a 20th anniversary gold edition. Here it is. Graphics card. It's one of the fastest ones anywhere, and I think it's like a $750 card. It's sitting over here in a box waiting for me to ship it to someone who wins this thing. And sorry, David, you can't have it, but yeah, so go to the website techreport.com, find this store. It's one of the top news items still, and sign up to win. And thanks to Asus for doing that. This is celebrating 20 years of making graphics cards, which makes me feel old, just because that's a long time to be doing these, especially because I think Yeah, mostly 3D ones, I guess. Wow.
Yeah.
Yeah. So let's not think about that. But okay, so I think the next thing we need to do, David, is definitely get in some questions from the chat because
Yeah, I was
folks
just
have been
about to ask about that.
patiently waiting. So let me see. Let's go. Okay, from what I read around the web, it looks like this is Chuckula. It looks like
Okay.
Project Skybridge is being pushed aside. Any thoughts on that?
I mean, I think I had a tweet that put it pretty well, right? That Project Skybridge turned out to be a bridge to nowhere. I mean, you know, the advantage of having a socket-compatible x86 and ARM core is really around infrastructure and design effort, right? You don't have to redesign your motherboard, but, you know, there's so much difference in the system to start with from the software side that, you know, I think what they said is customers weren't interested, and that's not surprising to me. I mean,
Yeah.
my personal suspicion is that the reason they're doing a custom ARM core is not because they expect to be selling ARM chips on the open market, but that one of their semi-custom partners wants it in the future.
Right.
I mean, you know, in the context outside of cell phones, the ARM architecture is not an advantage relative to x86. It's a huge disadvantage because you can't run Windows. You know, in servers, it's a disadvantage because it's new, it's an immature ecosystem, you know, it's not a first-class citizen.
Yeah.
So, and I think this is ultimately what led to Dirk Meyer getting fired, is he sat down and did the same analysis that Intel did and said, you know, the instruction set doesn't matter, the advantages seem to be in x86 favors, let's just stay the course. And I think that is true for a lot of the markets that AMD participates in, and they're never going to get into cell phones, so it's sort of a moot point.
Yeah.
You know, in tablets it's debatable, but you can run Android on x86, and, you know, I mean, you're probably at a disadvantage there, but, I mean, frankly, the tablet market is sort of evaporating a lot faster than people thought it would.
Yeah, it has been a little bit weird. I don't know that it's going to evaporate, but it's definitely not the case that people are buying phablets, and you know, honestly, I think this year we're going to see laptops make a little bit of a comeback.
I hope so.
Yeah, they've not been a good place. Okay, here's a question from Punk User, that's Andrew Lauritsen, by the way.
Yeah.
So we kind of addressed this, but do you have worries about building a high-performance desktop core on presumably a low-power optimized fabrication process? And we kind of talked about that. AMD doesn't have its own fabs. They don't get to do the optimization that Intel does. Is that a concern? I'm going to be snarky and say Intel has been optimizing for low power in its last several processes and shows no signs of doing anything but that. But maybe tell me why I'm wrong.
No, well, so I mean, you are wrong.
Okay.
And you know, for microprocessors, let's just take a step back and look at the two guys who really do high performance, and that's IBM and Intel. And one of the things about both of them is they use a lot more metal layers, and it's tapered. So if you look at an ASIC design, and Sam Nafziger talked about this a bit at ISSCC and other places, a standard ASIC metal stack is a ton of fine pitch layers and then some like 4x layers higher up. And that's kind of what you get because the design tools can handle it.
Mm-hmm.
At Intel, they have on 14, they have a 52 nanometer layer. They have like a 70 nanometer layer, I think. And then they have 80 nanometer layers and then 160. And then they have this, you know, like 17 micron upper level metal and stuff in between. And so you get a lot of metal wiring that is very good for going long distances over the chip, which is what you need for a CPU. The other thing is, you know, Intel did air gap dielectrics. And that it gives you a better insulation around the wire. Your signal transmission gets a lot better, and that will boost your ability to get CPU performance and frequency and so forth. And so there is a disadvantage to AMD in that they will not have air gaps in all likelihood, because the metal interconnect stack is the same thing as TSMC and Global and Samsung's 20. But
So,
the real question is, how much of a disadvantage is it?
right.
Is it 5%? Is it 10%? And the other thing is, there are other things that they can tweak to get higher performance. I mean, IBM is actually going to be moving to bulk silicon made at global foundries in the at 10 nanometer and beyond, I believe. So they've figured out some way to get high performance. And the other thing is AMD could just bite the bullet and say, we're going to get more metal layers and that'll hit us on cost. But, for servers, it's worth it.
Right. Here's I just pulled up a couple of pictures of some of Intel's metal stacks at 22 and 14 here for everybody to see.
Yeah.
And you can see some really big layers and then going down to the fine pitch stuff.
Yeah.
And so that's what you were talking about.
That upper level metal, I think that's actually unique to Intel, and that was like one of the things that let them do the power gating, the fully integrated voltage regulator, and it's really impressive that they got that to work.
Right. And I think that AMD did some disclosures around that they're doing integrated voltage regulation in a future APU, like post Carrizo, which Carrizo is the one that's not quite out yet.
Yes, that's correct. So Carrizo, they changed how they're doing power gating. I could get into all sorts of speculation on fully integrated voltage regulators. But the bottom line is that they changed how they're doing power gating, and one of the reasons is that they wanted to use some of the chips for internal testing of different voltage regulation techniques. And there's a lot of options out there. They might be using linear regulators. That wouldn't surprise me. That's very easy to overlay on top of a power gate. So like the IBM's Power 8, they have, each core has 4 voltage rails inside of it. And those are all provided by linear regulators. That's not a great fit for things outside of servers. For client systems, you kind of would like to have something that isn't a lossy converter or quite as lossy, but there's capacitive solutions, although those aren't area efficient, and maybe they'll do some sort of inductive solution. But there's options out there.
Okay, I've got another. This is an AMD slide on Carrizo, David, that actually shows a CPU centric tapered metal stack and then a GPU or general purpose oriented one, and you can see the big layers are a lot smaller on the general purpose one, and that you lose that when you don't have a CPU specific process. And they're touting it as an advantage for density, and it is, but it's not an advantage for building a really high performance CPU for the reasons we discussed. So let's see. Here we have a Combat Ineffective asks, do you see a future where HBM supplants traditional DRAM in desktop systems?
It's a good question. Probably not. The challenge is HBM is going to be expensive, and so I have this Asus laptop here. I think it has 4 or 8 gigabytes of memory. And every time I can Control Alt Delete and find out, but this thing is always out of memory, and I'm always saying you're about to run out of memory, like start closing applications. And it's a 4 gig laptop, so could you do it? Yeah, but the latency on HBM is probably not great for a CPU. The cost is not great for a large part of the market. I would think that what you'd be more likely to see is maybe it's possible, but I would expect more use of like LPDDR, frankly.
Okay.
In the mainstream, and maybe
we have DDR4, which is low voltage, right? I mean, that's kind of the next step for the desktop.
Yeah, I mean, but on the notebook side, LPDDR is definitely. I mean, it could be advantageous to use it. I think it's tough. We don't know what the latency of HBM is, and if it's really designed for GPUs, it's not going to be in the 50 nanosecond range that we're used to.
Right,
and I could be wrong.
Right, that's the first version of it too.
That's also true.
There are other possibilities where you do something very similar with some stacking and an interposer, and you have a memory that's more appropriate for a CPU, right?
Yeah, I mean, you can certainly do that. I think it's very, very expensive. I mean, if we look at what Intel did with Crystalwell, no one was willing to pay for it except Apple, really.
That was the external 128 meg SRAM cache that they stuck on the
DRAM. Embedded DRAM.
Cache that they stuck on the same package as the Haswell IBM.
Yeah.
No, it's Haswell.
Yeah, and the thing is, though, that's really not all that fundamentally different in some ways from HBM, except that, with HBM, you're not using Intel silicon for the memory, so maybe the margins can be a bit lower, but, the point still stands. I mean, the interposer is not cheap, the DRAM is not going to be cheap, and could you see it for a very small subset of the market? Maybe. But there's an awful lot of the PC market that's really cost sensitive. And unfortunately, that tends to drive things, right? Why is it that people still have hard drive only notebooks? I mean, that's just bad, period.
Yeah, I mean, I guess that probably my expectation is that this question would be more about like high-end desktops than about the bargain basement.
Yeah, but a high-end desktop, you might want 16 or 32 gigs of memory.
And then it gets to be a capacity issue. I think the way that this works, if it works, is that lots of people decide they want it and they buy enough that it helps drive costs down, right?
That's right.
And that could happen if there are clear benefits on a higher-end desktop.
Yeah.
So,
I mean, and I think one of the things that is worth mentioning here is the art of managing disparate types of memory is tough. And so one of the attractions would be not having to mess around with really complex memory controls and operating system visibility of different pools of memory with different characteristics. Because, I can tell you about all sorts of things that do and don't work. And, telling the operating system to worry about, operating systems barely have NUMO working. Like now you want to have NUMO within a single socket, and where it's not just like one is higher latency than the other, but one is fundamentally optimized for bandwidth and one for capacity and one for latency. Like you're going to give someone at Redmond like an infinite number of seizures.
Right. Okay, let's see. I think we have one other question, and this is about something that you said on Real World Tech. So you made reference to a speculative 3+3 ALU AGU configuration. Is that for Zen? Would this not be equivalent to the K10.5 chip? And how do you see this playing into the claimed 40% increase in IPC in Zen?
Right.
This is Tech Guy Max C.
Right. So, we were sort of speculating about those leaked slides and the leaked and faked slides, I should add.
And so this is the internal microarchitecture of Zen as you guessed it might be?
Well, no. I mean, I was looking at the slides and saying, well, okay, what can we, if these are true, what can we take away from it? And so one of the things to remember is the reason why AMD went with that arrangement in the K7 and the K8 is that in x86 land, you have this fundamental idiom of load op, right? look at AVX. You can do a load, a floating point multiply add that sucks in two other operands from registers and then write it out. You know, that's the idiom of x86. It's a load op architecture. And so having a balance between ALUs and AGUs makes a lot of sense. Now, you can have more ALUs than AGUs, sure. And like what Intel does with Haswell, you know, they've sort of got one that's, you know, will handle branches and other things outside of your ALUs. You know, for Zen, I think the really big question is how many load store pipelines do they have and what's the arrangement? And related to that is how many floating point multiply accumulate units do they have? Right, and some of this comes to, do they want to compete in HPC? If they want to compete with HPC, they probably need to have two FMA units. And if they need two FMA units, they need two load ports. And so then the question becomes, is it, you know, two load or store ports, or is it two load plus one store, or what's the arrangement there? And, you know, I think having three ALUs is fine. I think having three AGUs would be a fine choice too. But, you know, then you're sort of looking at something that looks an awful lot like Haswell in many respects. But, you know, the other disadvantage AMD has is Intel has amazing SRAM designers. So, you know, trying to clone what Intel does in some ways may not be
right, the best architecture choice. Yeah.
Right. I would expect AMD to play to their strengths, or whatever it is, you know, minimize their weaknesses, if you want to put it that way. But I wouldn't expect something that looks exactly like what Intel's produced. But, you know, if they want to compete in HPC, they'll certainly want to have two FMA units. So that does tell you a bit about what they're going to want to do.
Okay. Let's see. I don't know if we have any other questions from the chat here. Guys,
Really?
if you're in the chat and you have questions, then let me know. I think we pretty much have covered them based on what we've compiled here. There's a question, why do they need all this color compression when they supposedly have huge memory bandwidth? Because more is always better on bandwidth?
Yeah.
I don't think that's hard. Sorry, Chuck. You have better questions earlier. I need to degrade him, but
tactful, Scott. Very tactful.
Yeah, you know, I think that's pretty much it. Let's see if you guys have questions, get them in now.
Yeah, I mean, so the other thing is, you can look at this as a play towards VR, frankly. While we're kind of at the point of saturating PC graphics, and you can make that claim. Whether it's right or not, I don't know. But you can't even get close to making that claim about VR. If you look at how much bandwidth and flops we want, you know, it's at a bare minimum 50x more than what you're going to want for a standard PC display. And realistically, it might be hundreds of x more. So, you know, we don't have anywhere close to enough bandwidth for, you know, really cutting-edge applications.
Yeah, I mean, right now, 4K is clearly not a solved problem. The 4K graphics is bad. Like, on AAA games, the fastest graphics card, the Titan X, is usually okay, like, not terrible, but it's not great. And so that's that. The other thing about VR that's interesting is that you really need to get your pixels back quickly too. Like is so important. I think that's going to drive some architectural changes eventually in GPUs if that becomes the workload that drives development, or one of the workloads that drives development.
Sure. Well, it's not just that. I mean, you're also going to see like real changes in the rendering pipeline. So, I mean, you were at dinner with Andrew and a bunch of the other guys, and you were sitting right next to Warren Hunt, right?
Yeah, I think so.
Yeah, so, you know, he's one of the lead scientists at Oculus, and this is a dinner.
I was across from him. Yeah.
Right. But yeah, it was a dinner I put together. And, one of the things we were talking about is that, I'm just going to throw out some rough numbers here. If you look at the resolution that the eye can see statically, like without taking into account some of the really nice exotic tricks that are visual system and mind play, in your fovea, you can get about 1,800 pixels per degree visibility. Like, that's just insane. And so one of the things that people are going to end up looking at is foveated rendering, where instead of looking at a panel that's a uniform display of, here's a pixel, here's a pixel, here's a pixel, you're going to have rendering that's at higher resolution for where I'm staring, and then the resolution falls off as we get further away because, my peripheral vision is simply just not as good as what I'm staring at. Like, I don't think most people can read things out of the corner of their eye, but, we can read super tiny text if we're focusing on it. And so you could look at non-uniform rendering, which then now you might start asking yourself, well, gosh, what kind of display do I want? And that might look really different because you need high-density pixels, or you need to be able to sort of project at the eye.
Right, and there's some, I've seen some interesting demos of some of the projection stuff. But okay, we should wrap this up because we've been going at it for a long time. We got a follow up from tech guy Max C.
All right.
So he asked about the Zen having only a 3+3 ALU AGU arrangement. How can they achieve 40% more IPC in desktop workloads if that's the plan?
Yeah, so, the truth of the matter is that ALUs are not a bottleneck. I mean, ALUs are just not really complicated pieces of machinery. The problems are in the load store, the problems are in the branch prediction and the instruction fetch. So if we look at like what Intel's done there, right, things like the UOP cache make a big difference. Good branch predictors make a huge difference. And Intel has better branch predictors than pretty much everyone. I remember talking with Andy Glue and other folks, and here's a better example. But, Andy always said that Intel had better branch predictors than what a lot of the guys did in academia. And I was at ISCA, which is a computer architecture conference for academics and industry. Like I showed up there and they didn't even know what to do because they're like, press, what's that? And, I'm sitting at a dinner table with Daniel Jimenez, who's like, there's like two academics who are experts in branch prediction. He's one of them. And he's like asking me if I know what Intel does because I'm watching them. And he's like, I really want to know because they have some really good stuff and they just don't talk. So there's a lot of things, and prefetching is something that can be improved. Again, the cache hierarchy for Bulldozer was terrible. The L3 cache basically didn't help. It was so high latency. Mm-hmm. The L2 cache latency, AMD's L2 cache latency on the Bulldozer derivatives is like on the order of 18 to 20 cycles, which, Intel's L3 latency is about 25 to 27 cycles. So simply fixing your cache pipeline and, going to 2 load and 1 store and better branch prediction and adding SMT could do a lot of that good.
Right.
No question.
So what you're saying is there's plenty of opportunity to improve around the execution units and other. Yeah. Okay.
Now, do you go to 4 ALUs? Maybe. Look, Intel did it in Haswell, so there's clearly an ROI for some workloads, but there's also a question of how big of a die do you want to have, right? Intel's cores are very big, mm-hmm. and AMD may not necessarily want to go down that path.
Yeah, no, I think there'd be some wisdom in them building something that's a little bit lighter weight.
Yeah,
and for servers, you can just then add more, and it kind of works out. So
exactly.
Yeah.
The other thing is, and this goes back to Andrew's question, is how much of a performance deficit is AMD really at due to process technology? And the answer is they're always going to be at a deficit of some sort. And, maybe the takeaway from that is that if I'm Jim Keller, I don't want to aim for beating Intel at performance because that's essentially impossible given the resources at AMD, given the fab disadvantage. I don't think that's the solution. I think the solution is simply be good enough. And there's probably a large number of customers who would be loving to buy from AMD, would love to have another option if AMD could get within spitting distance of Intel. Now, what's spitting distance? Is it 30%? Is it 20%? Is it 10%? That's an argument for another day.
Yeah, it's 15%, dude.
Okay.
I'm sorry, I had that answer. I didn't know you wanted it.
Oh, I didn't realize that was how far you can spit. I'll have to make sure I keep further away from you in the future.
I thought I'd let you know. No, I don't know. It seems to me like something around that, though, is like a nice place to be, right?
Yeah,
because
that's right.
What you have is credibility, and if you're trying to be a second source, second supplier, and you can be within 15%, you can still sell a chip with probably good margins, which is what we talked about, right?
Yep.
You can sell something that you can make money on still. Get past that, and it starts to look a little bad because Intel can discount and things get difficult. So anyway, I see what you're saying, though.
I mean, the other thing is, right, that a 15% performance deficit in CPU alone, I can see making that up by having a really phenomenal GPU. The problem is you can't make up a 50% CPU deficit with any sort of GPU. It just doesn't matter.
Yeah.
Right? You're not even in the right county. Yeah.
Yep. I mean, depends on what you're talking about. That's more of a client thing.
Oh, yeah. No. I mean, servers, a performance deficit will definitely manifest itself as a real hit in prices and what you can get.
Right.
But, yeah.
Okay. Well, you know what? I think we should probably call it. I appreciate you coming on and joining us and being willing to talk for so long.
Absolutely.
And taking questions from whoever about whatever.
Yeah.
I think we pretty much have burned through the questions from the chat, and we covered a lot of ground. So thanks very much. We will have to do this again sometime soon.
Yeah, that'd be great.
Maybe around another big disclosure or when we have some kind of a new product to talk about.
Yeah, I think there should be, hopefully we'll get plenty to do. Right,
yeah,
I mean, we've got
Skylake is coming. Yeah.
What are the other big things? Yeah, I guess, maybe Fiji, Skylake, and...
Fiji, Skylake, there's probably going to be a disclosure around the 10-nanometer process from Intel at some point later this year.
Yeah.
Which, like, you've got a lot to say about that, I think.
Yeah, I mean, I don't know. When I went out with my guesses on QPI, I had a really high hit rate on that. I was correct about a lot of things. I mean, so much so that Pat and Steve at Intel, like, they actually thought that someone had given me a red dock.
Right.
And, my speculation on Knight's Landing, I had some things right. I had some things wrong. I thought they were going to have an L3 cache because I thought they were going to want to make it coherent across QPI with the Xeons. It turns out I was wrong about that coherency, and therefore I was wrong about the L3. 3.5s, we'll see. I may turn out to be wrong, but at the end of the day, I can explain exactly why I thought that what I did. So, I'm happy to be wrong if I'm wrong in the right way.
Right. Well, we maybe that's a topic for another stream then.
Yeah.
So once we know a little bit more for sure from Intel about 10 nanometers, we can line that up with what you predicted and let you defend yourself. That would be fun.
Yeah.
So,
that's
all right,
right.
everybody on the stream, thank you for joining us as well, and we'll hopefully do this again soon.
Yeah. Have a good evening.